EECS 281, lecture number 24, strings and sequences. Okay, today we're going to talk about strings, sequences, some of the algorithms that are involved with them, and just some of the approaches that we have here. A lot of sort of smaller topics that we'll be talking about. Some key insights, however, into how hashing is done for strings. Before I get into that, though, I'm going to try to save us all a little bit of time in office hours. And let's talk about insertion. That's one of the heuristics styles that will work with part B of the project. We're trying to find a fast TSP solution. So there's a number of ways to do it. Using insertion is one of them. Not saying that you have to, but there's a discussion that just needs to be had. So I thought I would go with this insertion thing. And there's really two parts of insertion, right? And the first part is somehow we need to find a vertex that we're going to insert. And there's a bunch of different ways to do this. If we look at what that finding means, it can mean a bunch of things. So there's technically four of them that come straight to mind. There's one that's called nearest insertion, right? And we use this nearest, we find the nearest thing. There's another one that might sound scary, but it actually is pretty effective. It's farthest. There's arbitrary, and then one that's a little bit harder to understand. I find the cheapest, right? So I use one of these four methods or other methods to figure out which point I'm going to insert, and then step two is perform the insertion, and performing the insertion is the same for all four of these different methods, right? Perform the insertion. Okay, so that's how insertion works. Now, to be clear about this, there is a piece of work out on the internet here that is pretty commonly tracked down in 281. We'll check that out. It's this wonderful PDF here, someone's discussion of heuristics for TSP. And very commonly we see people using, there's another one. This is a greedy formulation that doesn't do insertion, which will also work. And then right after that, this is where people stop and end up with problems. And the problems come from the wording. If you look at the title of the site, it says, Nearest Insertion of Arbitrary City. So the confusion here is sort of the joining of nearest insertion, which is by definition how insertion always works. You insert the thing in the nearest place where it works. However, the arbitrary city aspect of it makes it seem like it's doing arbitrary insertion. So one of the confusions is oftentimes people will come to office hours and say, well, how are you doing your fast TSP that's not working? And they say, well, I'm doing nearest insertion. Well, no, most people aren't doing nearest insertion. Nearest insertion is a bit more complicated than arbitrary insertion. Or they'll say I'm doing arbitrary insertion, and this slide has arbitrary in the title. However, if you go look at step 1, right there in step 1, it says start with just one city, I, randomly chosen, then find J, for which the cost from I to J is a minimum. That is not arbitrary. That is a very specific point. That is the closest point in the set from I to J. That is not arbitrary. That is closest. So it doesn't really matter how you do your selection. you can do a hybrid method, because in reality, after step 1, then it says in step 2, just, pick anything arbitrarily. So this really looks like a hybrid method where the first item is chosen as the closest point, and then all of the items after this, the second item is, first item is chosen arbitrarily, the second item is chosen as the closest one to the first item, and then all of the rest of the items are chosen arbitrarily. That's a hybrid method. And it's okay, it works. Any hybrid method would work. It's just really complicated to program, and unnecessarily so. And it's easy to write bugs into it just because it's more complicated than it needs to be. So let's get back to how we find these vertices. In a nearest insertion, right? In the true nearest insertion heuristic, not the nearest insertion that's discussed on this particular slide of the PDF. In nearest insertion, what you're really trying to do is track down the point that is nearest to any of the points that are already in the path, right? And that, if you're not careful, is going to cost you n squared to find every time, right? So we would like to get this done in a linear amount of time, and the only way that you can do a nearest insertion and keep your complexity under n squared total is if you can do your find a vertex, your selection step. If you can do that in linear time, then you do a linear number of insertions or linear number of steps to do the insertion. You end up with this n squared thing. So in nearest insertion, what you need to do is you need to find the point that's closest to anything that's already in the set. And that can only be done if you maintain a sort of prims-like data structure in which you say, well, I'm going to start out with my first point, locate all of the points distances from there. Now I can find the nearest point to that, and just like in prims, when we find a new thing that we mark true, then we go back and update all of the things with relationship to the newly marked item. So if I take the first point, find everything as close as possible to it, or find their distances and store those distances, then when I find the new point, I need to update any distances that are closer to the new point than they were the old point, and that I can repeat. So that's nearest selection. Farthest selection is just the opposite of that, right? I'll pick my first point, find the distances to all the other points, take the one that's the longest. Then if I retain those distances and update all of the distances of the points that aren't included to make them farthest from any of the included points, that's how I get farthest selection. Arbitrary selection is just how it sounds. You can just randomly pick those things. And there's a couple of simple ways to randomly pick them. The first one is to just look at them in any order. Take them in the order given. They aren't sorted. So just go from 0 to 1 to 2 to 3 to 4. That's arbitrary. They were arbitrarily generated. Another way to really improve your arbitrariness, if that matters, or if that even means anything, is you could randomly select one. Out of the 15 remaining, I'll pick item 4, and then out of the 14 remaining, I'll pick item 7, or whatever random number generator that you can use there. That one would also work. As I mentioned, any of these selection methods will lead towards a successful insertion method. But doing a random number generation thing would be more difficult than it needed to be. Let me try to get I'm having issues here. The studio's breaking down. There we go. All right, so arbitrary, you can just pick them just from 0 to 1 to 2 to 3 to 4, and that one ends up being structurally the simplest to program. And then cheapest insertion is more complicated. In cheapest insertion, the cheapest selection is to choose the point that will cause the globally lowest insertion cost. Not to find the lowest insertion cost for that point, but to find the point whose insertion cost is actually lowest between all of the things that are already in the path. So cheapest is not going to be under the same complexity as these first three. So these first three are pretty easily big O n squared, but the cheapest is bigger than that, right? I think it's n squared log n. So that's what selection is about. You find a point. Then the insertion portion of it is, if I've already got a collection of points that are in my current path, I can think of them as a small tour. And then the insertion says, if I already have this tour of 6 points, or whatever my K is so far, 7 points, and I'm adding a new point, there's one point where I can insert this between two cities that is the least expensive. So that's how all the insertion methods, they all use the same insertion step, which is minimize where I add this new city to the tour. So that's the same across all insertions. But then the name of the insertion method comes from how selection happens. So nearest selection or nearest insertion is different than arbitrary insertion. Arbitrary insertion is the one that you can use. And arbitrary insertion, in terms of some of my sort of just anecdotal testing, I've seen farthest insertion with generally the best work there in terms of shortest paths. It's still n squared. After that comes nearest insertion. So let's do it like this in terms of effectiveness. And then finally, arbitrary insertion comes in after near the nearest and farthest. But any of the insertion methods will work. As long as you keep your complexity within n squared, they should be fast enough and small enough memory footprint to get you full points on the autograder. So be aware that our first step here, when we're talking about the nearest insertion of an arbitrary city, if you're going to use this PDF, all you need to do is cut out this portion of it. Cut out that portion of step 1 and it works out just fine. Start with a partial tour of just one city I, then given the partial tour, select a city K that is not yet in the partial tour, and you can insert it from there on, right? So that works, and then there's some other sort of mechanics that can make a simpler program version of this for you, but in terms of the theory of the algorithm, cutting out this selected text here, that's the problem. All right, on to the show. Let's get back here and go there. All right, so talking about string algorithms and why should we even bother studying them? From the bird's eye view, we see that strings are just character sequences. I was always taught that a string is just how you string together characters. So when we learned C in the early days, there wasn't a string type. And if you look in C++, there isn't a string type in C++ either. Our built-in types are just integral types and floating point types, right? So we've got characters and we've got arrays. So C-style arrays, or C-style strings as we call them, are just an array of characters. And that's all that C++ even supports. It takes the STL to give us sort of a string object, right? But if you look at it, a string then is just a bunch of characters strung together. That's why I was explained to me as what a string is. So each one of these characters are chosen from some alphabet, and you can really get into what this alphabet choice is. One of the things that we use, obviously, is the ASCII character set. We move past that as we add further language support, as we start using Unicode that gives us many different languages. But every language has some set of characters that build that language up. So we think of our string as this collection of characters. The characters are chosen from some set of legal characters, and then in reality, then all my string algorithms are just array algorithms. They're just algorithms that work on a sequence of things that are stored contiguously in the case of strings. So an array of characters is still the underlying data structure, even in a C++ STL string. Why is this special? Well, we've got a lot of tasks that sequences and strings give us that we do often, searching for things, comparing things, and we'll look into some of those things. The applications that really come into interest, of course, is with human readable text. That's what we're talking about, our main character sets, ASCII and Unicode. One of our ancient character sets known as EBCDIC, EBCDIC. That was how the anagram, not the anagram, the acronym was for it, and we just pronounced that EBCDIC. But that one was an older one that is no longer really in use. There's names and labels as we look up people and files and license plates, things that get stored in data that is more expressive than, say, an integer or a floating point number. And DNA analysis, that's another one. If we look at DNA analysis, and if you ever want some great information on this, grab Dr. P, and he can tell you more than you can imagine. Right? That's where he did his PhD work. And DNA analysis has to do with really looking at these chains of molecules, right? The DNA is this molecule that's wrapped up with these sequences. I can't even get the things right. There's alleles and all kind of fun things like that. But the way that they do DNA analysis is to just treat the DNA as a big string. And it's this collection of characters, and they're chosen from an alphabet. It's far restricted. It's not nearly as many characters as we think of using in English language. I think there's only 4 characters. But those 4 characters in all of their different orders are what make you, you, and make me, me, and make birds, birds, and all those good things. So that's why we study string algorithms, because their efficient use is important to science, to all of our stuff. So we won't be looking at sequences of objects or doubles. We're just going to stick into those integral types for now, and that's good enough. So working with strings and sequences, if I am given 2 strings and sequences, some common questions I have is, first and foremost, is are they equal? That's one I see all the time. I've got this, I'm trying to find this, I need to know if it's equal. When I'm not trying to go for pure equality, I'm just trying to get a proper ordering, then I need to know which one would show up first, possibly in a dictionary if you were to, where I'm looking for less than, or maybe a less than or equal to. What do they have in common? Me trying to find substrings. Finding out where strings differ. Now that's an amazing one. Just to find out where differences come in, I think one of our primary uses of that aspect of string algorithms in 281 is people using diff checker to check out if their results are equal to the given test results. And then that's how the autograder, most of the autograder judges apply some sort of diff style checker there. So that's one. But to go beyond just the simple version of diff, if you use the program diff, which is the heart of what diff checker uses, and it shows the differences between 2 files, that difference historically has been called a patch, because you can take a patch which has the differences between string 1 and string 2, and if you apply the patch to string 1, you get string 2. And that is the heart of Git. Git is just this massive system that does all of this very slick diffing. And so every time you make a new commit, what diff does is says, hey, well, here's what the code looked like before they committed, and here's what it looks like after the commit. If I run a diff and store that patch, then I can easily go back to a previous version, because all I can do is apply or remove a patch from a piece of code to go forward or backward in time. And so working with strings and sequences is 100% what Git does. And Git is very important. You should be using it. And if you're not using it, you should be learning about it. Another thing that you might do with more than 2 strings, we've got many strings, you might be looking to find them in some particular order. Dictionary order, also called, get this right here, lexicographic order. I try not to say that word too many times. It just makes me stumble. Lexicographic. That's dictionary order. So given many strings, trying to put them in dictionary order, that's, I can't even say that. Put them in dictionary order, that's a common strings task. Because once I've got things in order, we know how much easier it is to search them. When I know things are in order, then I can use binary search. My searches speed up greatly. Other things in working with strings and text. Given a couple of strings here, let's say I've got something that I'm looking for, P, and something that I'm looking in, S. We'll call these two strings P and S, and if you wanted to be clear about what they really represent, that's looking for the needle in the haystack. So P is the small thing, S is the haystack. One of the things we can be doing is trying to find instances of P in S. I might need to find the first one, or I need to find the last one. There's functions that do those sort of things. Find the next one. If I've got one now, find me the next one. Or I could be trying to tabulate all of them. That's common string work. Another variant that I can do when I've got a fixed search body, if I'm going to be doing a lot of searching, I can do some pre-processing of P, right? If I can pre-process P knowing that my haystack is never going to change or changes very seldomly, I could use that to speed up a lot of my subsequent searches for P. I'm going to pre-process P and then use that pre-processed P to do multiple searches within S, right? Another thing, we talk about strings and texts, and it seems like it needs a distinction between what one of those is. So a text is really a string that has separators in it. So we can think of a text as being delimited into words with some delimiter character or characters. So once we have texts, now we can start looking for phrases, or we start thinking of sort of our P's and S's, where the P is now a word that I could be looking for. Moving forward, I can say that a text corpus is now a collection of documents. Each of those has a text in it, of course, and some additional meta information, possibly title, some other attributes, author, copyright, URL, other media, who knows. So a text corpus is a collection of documents. So given a text corpus now, I might try to search in a text corpus, which is going to take some search string and find all of the documents that have the search string in it. You'll be looking sometimes for exact matches, things like names and IDs. You really need to get those exactly right. Other times you can have approximate matches, where you're looking for something that's similar that might catch, for instance, a spelling mistake, but you wanted to get something like that, and a close search will be nice there. And there's also cognate matches, where you do a search, for instance, for a mic, and you find all the mics and all of the Michaels, or things like that, where you might do a search for COVID and find things that also match coronavirus. So those are cognate matches. That's a little bit different than dealing with misspellings and exact matches, but it's also an aspect of string searching. So there's a fairly large industry built upon finding text within a text corpus. If you think of what a collection of documents the World Wide Web is, I think you see where I'm going there. So another thing that you could look at, so our Project 1 submissions. How do we find pairs of similar programs? There's cheat checking that goes on. That gets sent through software that does matching of portions of texts in multiple documents across these corpuses. If you think of every submission as a corpus, it's a collection of documents, and then we're trying to compare corpuses. Another thing that works with strings and text is text compression. We like to compress text. It's usually fairly easy to compress text, more easy than it is to compress binary data. Very often binary data is already fairly densely packed. But if we look at the way that text works, we often use much less space than we need, right? For instance, if you look at the English alphabet, you see if I've got 26 characters, even 52 characters, when I'm talking about capital letters and lowercase letters, if I'm just talking about letters, I think if I stick each one of those into a byte, and since a byte can represent 256 different values, me using 52 values per character is really telling you that there's more space there that I could be using, right? So compression kind of works on this. It tries to use smaller versions of those characters. It will sort of look at sort of commonly used characters and say I can take the most commonly used character and make it the shortest string possible. That's one method of compression. Another method to do it is to find repeated words, and then rather than use 15 different versions of the. It'll try something that's a bit shorter and say, if I can get the taken care of in one byte, and that representative byte is something that I can go back into a lookup table and say, when I see this byte number 1, that's the most common word, replace that 1 with the. And so that's a text compression method. All right, so here's a simple job interview question. As we're looking at sequences and things like that, it's going to be useful as we move forward. So what I'm going to do is show you one fruit at a time. And there are 4 different fruits. There's apples, bananas, oranges, and pears. No other fruits. So the question is, if you can stop when you detect a repeat, how long in the worst case is it going to take for you to figure out when the repeat happens? So with n being the total numbers of fruits, what am I looking at? So if I'm showing you n fruits of these 4 choices, how long does it take before you catch a repeat? Is that something that's going to take me linear time? Is that going to take me logarithmic time? Or is that going to take me constant time? Or is it something else? Let me think about that one. So remember, n is the total number of fruits, and the type of fruits, the total number of types of fruits here in this case is 4. So if you think about this, we don't need to see all n of them. I just need to see at least 4 of them, right? So I can say that in constant time, I can figure out when a repeat is going to happen. And this is brought to us courtesy of the pigeonhole principle. If I've got 4 different fruits, I can just have an array of size 4, and after I've inserted no more than 4, the 5th insertion has to go into one of those previously chosen fruits. So it could be less than 5, but it could be no more than 5, regardless of how many total fruits there are. N is not related. So I'm going to call this one pigeonhole principle constant time. All right, here we are at our DNA. All living organisms encode their information in the sequences of this simple chemical substances, right? Your DNA is just some combination of your parents' DNA. So a DNA structure is defined by this nucleotide base pairs. Once again, refer to your closest Dr. P. But in these base pairs, we have just this real limited alphabet. These base pairs are all formed out of collections of 2 words or 2 characters from this alphabet, and there's just A, C, G, and T. So we can see a base pair over here. They've got names like adenine, cytosine, thymine, and these base pairs are just combinations of A, T, TA, C, G, G, C. And so when your parents' genes get together, each one of those things pairs off and makes a decision whether it's going to take half from your father or half from your mother, and that's how we get the new you. And this gigantic collection of genes is so large that no 2 of us ever end up the same. It's pretty interesting. Each one of these genes is just a subsequence in there. So you can think of a gene really kind of as like a word in a text or a word in the document. Each one of these genes is a subsequence of the overall DNA sequence. So in that case, we can use these string algorithms to compare chromosomes. We can use it to look up genes. We can use it to assemble sort of long DNA strands from short sequences to do comparative analysis of historical things and the way things might be going in the future, and all manner of scientific goodness that comes out of DNA and string-based algorithms. As we look at our data structures here, we're going to be looking at individual strings, first of all, to see how these things relate in C and C++. So in C style, we talked about that as just being an array of characters. So for every character, I've got a byte, and then at the very end, I need that null terminator. All of the string algorithms just purport they're going to start working on characters and keep working on characters until they hit the null terminator. So our overhead in a C-style string is fairly light. We've got one pointer to get us to the beginning. We have to have an address where things go. Then we've got all the bytes of our string, and then the additional null terminator at the end. In our C++ style string, we've got something that's a bit more complicated. We've got now in the most recent version of G++, or the STL standard, G++ standard template library, we end up with something that looks like a couple of pointers. However, it doesn't quite give you the full picture there. The modern string ends up taking 32 bytes because it's got sort of like these two pointers, and then it also has a small area of memory within the object itself. So this is how we've got these two pointers in the string object, and when the string is short enough, those two pointers just point to within the object itself. This is how we get some pretty nice speed in our GCC 6 and beyond. But when the string is too long to fit within the 32 bytes, then those same two pointers just point to somewhere on the heap. So we get some dynamic memory there sometimes, and so it's a pretty complicated object, but it makes it to be really fast. All right. The complexity of size, then, because we've got these two pointers in a C++ string, is we can always just subtract those two pointers, as they are pointers to contiguous memory. So I get that constant time calculation of size in a C++ string. In a C-style string, there's nothing ahead of time that's going to let you know what that is. So to check the size, you just have to start at the beginning and keep looking at the next character and the next character and the next character until one of those characters is a null terminator, and then you stop. So it's linear to get our size in a C style when it's null terminated. When it's object oriented, because we've got pointers, we use those pointers to just do it in constant time. In C style, of course, our ASCII characters are built in. So I've got a limited alphabet. In C++, these templated strings allow us to use many alphabets, so it's configurable. That's pretty nice. Most of our operations and algorithms in C style are just pointer arithmetics. You can see those things in standard libc functions. In the object-oriented world over in the STL, we've got methods that are sort of string methods. There's other operators that can be used. We've got standard libc++ functions, STL library functions. So that's kind of a bit more useful object there. So as we look at sequences, we think of them really as things that I can iterate through. So a sequence in the STL's term is really just an iterator range. I need a begin and an end. And C++ strings support both begin and end as members, and they also support standard begin and standard end if I wanted to call those as well. As we look at more string-related data structures, we have some specialized containers. Dictionaries allow us to add and look up words, remove them. Those work out for storing strings. Excuse me. Other things that we might use, we can share strings with strings with shared fragments. Some words that are sort of common prefixes, we can use things like that. We can come up with specialized containers to help us to work when we've got multiple strings and save some of our processing time. If I know that all of these 40 words begin with the same prefix, I can save the prefix work, and then I start doing my string comparison operations after the prefix. How do we check sequence equality in the STL? This is something that there's no magic bullet for. A sequence comparison needs to be compared an item at a time. So oftentimes students ask me, is there they're asking for some magic function that I can just use from the STL that does things faster than they would. And oftentimes there is something that does it faster, but only slightly faster. If you're working with characters, the rule of thumb is you got to work with all the characters. You can write your own loop to go through those characters to do some comparison or some searching or whatever, But if you're thinking that there's a library function that can do that lookup faster by not looking at all the characters, you're mistaken. It might be slightly faster due to implementation skills of the library programmer versus you, but it's not going to be orders of magnitude faster. Even as I read a C-style string in or even a C++ string object, they're doing fundamentally the same things. So I can do this sequence equality in the STL, and I've got this 3-iterator function, equal, right? And what I need to do to determine whether or not these things are equal is I need to know where the first string starts and ends, or the first item in the sequence 1 starts and ends, and then I need to know where sequence 2 starts. I don't need to know where sequence 2 ends, because this equal is just going to return to me where this equality works out, right? And so if I've got some prefix here, for instance, if input 1 is just a subsequence, I can still find that in a longer input 2, because input 2 doesn't come with a last. We don't know where input 2 ends. We don't care where it ends. We just know that if we're trying to check a sequence 1 within sequence 2, that the STL is not going to protect you if you look for a longer sequence within a sequence. Look for a sequence that's longer than the target that you're looking in. So in this case, we don't need input 2's last, because it is assumed that input 2 is long enough to at the very least contain all of input 1. So I'll start at input 1 first and go to input 1 last, and I start looking from input 2's first. And as long as they're the same, I keep going. It's going to return true if everything in the range first 1 to last 1, half open interval, is equal to everything in the range first 2 to first 2 plus last 1 minus first 1, right? So that's a prefix check, essentially. Returns false otherwise. We can say that two ranges are considered equal if they have the same number of elements, and for every iterator I in the range, first 1 to last 1, if I dereference I, it's equal to dereferencing what's at first 2 plus I minus first 1, the offset, basically. That's just what you would that's what you would expect sequence equality is. Here's the standard library function, though, equal, that works with any sequence. So this is interesting. You can use this with strings. I can pass in string to this. Or you can use this with a collection of zombies, as long as you've got an operator equals defined for this. So this is sequence equality in the STL. This is how it might be written. You can see that I've got my incoming iterators here, 2 from the first sequence and 1 from the second sequence. And this version uses a for loop with no initialization step. That's why we've got that blank area here. That means we don't need to initialize it. We're just using the iterators given us, first 1 and last 1. That's our comparison step. When first 1 is equal to last 1, we've reached either the end of the first sequence or we started with an empty sequence. Then every time through, I'm going to update both first 1 and first 2. So that's what we see here in the third portion of the for loop. This comma in between allows us to combine these two operations. So in this case, the iteration step of the for loop moves both the first 1 iterator and the first 2 iterator. Then while we're in the body of the loop, we're just checking to see if what's at those 2 iterators is equal. If it's equal, we move on. If it's not equal, we return false. Eventually, if we get to the end of the first sequence without having run into any problems in the second sequence, we can just return true. So, in this case, as I mentioned, input 2 has to be at least as long as input 1. If it's longer, this function doesn't say that they're not equal, right? So this one is going to take grass and grasshopper and say that yes, they are equal, because grass is the prefix of the string grasshopper. So it doesn't give you sort of the equality that you might be thinking as pure string equality, meaning grass and grasshopper are not equal. They have a similar prefix, but this equal is doing a sequence equality that isn't bounded inside of the search target, right? So be aware of that. How could you implement this function? Is a job interview question at the bottom. Implement a variant of this function that takes a customizable comparator. So in this case, we see that we actually use the operator equals equals. And we talk about trying not to use operator equals equals on our own object as much as possible, or any of our comparison operators, just because it sort of locks you in place. So the job interview question here is implement this function with a fourth parameter, that fourth parameter being, of course, a comparator between things within the sequences input 1 and input 2. Here's an example of using this sequence equality piece of code here. We've got this equal function that we just looked at, and this is being used to check whether a string is a palindrome. That's pretty nifty. So as we look at it, we see that equal takes the same three parameters: where the first string starts, where it ends, and where the second string starts. And in this case, it's gotten tricky. It's used the STL in one of the ways that the STL has set itself up to be used. I talked about earlier the use of these reverse iterators. A reverse iterator is designed specifically so that you can move from right to left by incrementing. By plus-plussing, you can move from right to left. Normally, we think of plus-plussing moving us from left to right. So then this is palindrome function is just a simple call to equals, because we start at the beginning of the string and we go all the way up to the middle of the string. That's where the first string is. The second string that we're searching for the first string within is actually just the original string, but from the reverse end here. So this R begin gives me the end. So it kind of is like looking like if I start from here to here in the string, and here's 1 going that way, and 2 is actually going that way because it's got an R begin. Every time if I increment those two iterators and do a comparison, if they're equal, I will either get to a middle point that's empty, or if I get to a single character in the middle, I still haven't failed. Both of those are a palindrome. So that's a pretty nifty use of sequence equality there. You probably hadn't thought you could write a palindrome check in one line, but you know, it's the STL. They give us things like that if you look for them. So some people found rotate for project 3 when you're doing the B and E. Both of those could be done with one-liners, the same one line, well, different line, but the same function. There's an STL function, rotate, that would do B and E in linear time, and you wouldn't have to do anything other than give it the right iterators. Another chance for me to stumble on this word, lexicographic. We're going to talk about our lexicographic comparisons. So dictionary order sort of looks at this as the way that I spread things out. So an empty string is less than some non-empty string. That's our fundamental sort of vacuously true sort of thing. An empty string would be sorted before any string that has something in it. Then if I look at A versus AB, I see that a prefix string always shows up before its full string. So here the prefix is A and the full string is AB. So A shows up in lexicographic order or dictionary order before AB. And this is the same way that a Webster's dictionary is organized. And then here I've gone from AB to B. They don't have a common prefix, but the earlier character in AB is less than the earlier character in B, so AB comes before B. B, of course, comes before BB because really that's just this thing applied here. I've got a prefix of A and A. Here I've got a prefix of B and B. It's unimportant that there's something after the prefix that's the same as the prefix. It's just the fact that this shorter string, even though they've got the same start, comes before BB. BC, of course, now we've got two strings that are the same length, but they share a common prefix. And once we've expanded past the prefix, the string with the earliest character shows up first. And then lastly, we've got digits showing up after characters, at least in our dictionary order here. So the way that we do things, I would say that BC comes before BC0 for a couple of reasons, right? One of those reasons is because BC is a prefix on BC0. And the other reason is we're going to sort the BC0 after the BC anyway. So we have some overloaded comparison operators in C++. We've talked about the less than operator incessantly. So we use that because we don't actually need to implement all 6 of them independently. I say I can always do everything if you use your 203, and I use negations and reversals. It's good enough for me to use just one operator, this less than. Obviously, less than works for less than, right? It would help if I had equal to. So if I had equal, equals, and less than, I'm in good shape. If I needed to, I could always take one of those two and make anything else happen. So to get less than, I use less than. To get greater than, how do I get greater than? All I have to do is reverse the order of those things. That's how I can get is A less than B. I can use A less than B, or I can switch B less than A. That tells me is A greater than B, right? If I wanted to do greater than or equal to, I can invert less than. So greater than or equal to is the same as not less than. You know how logic works here. Less than or equal to is the same as not greater than. That's a typo. That should be not greater than. Less than or equal to is not greater than. There we go. And if I've got equals equals, I don't need to write not equals. I can just take and not the equals. There we go. So now, if I've got equals equals and less than implemented, the STL can do anything it needs. All of the algorithms that need more than one operator will be just using less than and is equal. So, the bad idea, of course, is implementing all of those operators. It just makes more code to maintain and makes the algorithms have to use more functors. In string comparisons, if I've got equals equals or lexicographic comparison, a common implementation trick for some class is to take some compare helper, right? I've got some compare helper that's going to take these two things, and I end up with what we call a three-way comparison. The three-way comparison gives us 0 when I've got equality, or a negative number, typically -1, when the left item is less than the right item, or a positive number, +1, when the left item is greater than the right item. If I do that implementation trick, then I can use my comparison operators and implement them with post-processing, and then the algorithm just works. Optimization for strings, we talked about this already. I mentioned the C++ string that we use now currently in the STL. It takes short strings that are less than 16 bytes. So I think the longest string you can represent inside a string object is a 15-byte string. So if you've got an ASCII string and each one of your characters is 1 byte, then you can represent a 15-character string inside the object. Anything above that you can still represent with the string object, but it then needs dynamic memory. So that's what I'm talking about, this string optimization. If I have a string that's a short string, 15 characters or less, it remains a stack variable that's close and fast. If I need to get to dynamic memory, if I've got something that's 16 bytes or longer, then I still have the stack variable, but the pointers inside of that stack variable point to something on the heap. So that's dynamic memory. And you don't have to manage this. The string object itself will deal with it. As the string gets set to something longer than 15 bytes, it will go get the memory, get that allocated, put the data there, and it works completely transparently. But when this change first kicked in, the semester that kicked in, we had to reformulate all of our solutions because string processing got an order of magnitude faster just because it wasn't going always out to the heap. Most of the strings that you use in the English language end up with words that are 15 letters or less anyway. So you really are only looking at using a longer string when you're talking about a sentence or more than that. We're talking about using dynamic memory. In C, we use our null terminator to simplify that prefix check, right? Because ABC0 is less than ABCD, that null termination just doesn't even, it's not looking for the null terminator there. It's just finding a value that's less than, because the ABC0, and I'm talking about the byte 0, not the letter 0. ABC byte 0 is less than ABC byte D, right? And so null termination handles that. In C++, because we can get the size in constant time, when I do a string comparison in C++, I can get a not equal to in a constant amount of time, but I just check their lengths. If string 1 is length 4 and string 2 is length 5, there's no way that those strings are equal. So I can use that optimization to figure out whether or not they're equal. So you can, if you think about that and you can say, I want to be using not equal to before I check it at a character level, you can get some speed up there, right? If you check first to see if they're not equal, the fact that they're different lengths can be done in constant time, and then you jump into a character by character check. So you can think of doing that. Where that might be applicable is in sort of a tiebreaker for zombie name, for instance. First was the arrival time, then the tiebreak on the name, then the tiebreak on the creation order. So if you can say if the names are not the same, we can do that in constant time before we even start dealing with the less than or greater than. So that's something that you can think of. You can use some optimizations if you understand the way these objects work. And also, there's a bunch of vectorized CPU instructions. Some processors, modern processors, have CPU instructions that are specifically designed for processing strings. Early processors didn't do that. They just sort of had a generic sort of calculating methodology. We say we can speed that up because we're so often doing this string work, whether it's comparing things. If we've got an instruction that speeds that up, then our whole life gets faster. So I mentioned this helper, this compare helper. This is what a three-way string compare could look like. This one takes in a couple of strings by const reference, of course. And what it does is it goes through and it's going to return 0 if they're equal. It's going to return less than 1 if the first string should show up in the dictionary. Sorry, less than 0, a negative 1. If the first string should show up in the dictionary first, it's going to return greater than 0, positive 1 if the first string should show up in the dictionary after the second string. So I've got my strings S0, S1, and you can see here that this is just a pretty straightforward loop. This first for loop is going to go in here, and as long as the two strings have characters in common, at least in distance, right? So the for loop is for handling the first K characters in common. So if I've got M characters in the first string and N characters in the second, so it looks like this: M characters in the first string and N in the second, regardless of which order they're in. So the for loop here is going to handle this part of the comparison. It doesn't matter if that's M or N or N or M, or if you want to look at this as S0 or S1. It doesn't matter what order they come in. I can look at this as S1 and S0. The for loop handles the part where the strings have the same number of characters up until one of those strings ends. And all it does is in comparison, if the string, the character in string 0 is less than the character in string 1, and that's the first thing, that's the first difference that we've seen. So we can then, without care, we can return a negative 1. If they are unequal the other direction, then we'll return the positive 1. So this for loop, as you can see, goes through each one of the characters in this sort of prefix area. if one string is a prefix of the other. That's why I call it the prefix area there. And it compares each one of those pairs of characters twice. So three-way string compare has to look at, is S0 I less than S1's I, and then it turns around and says, is S1's I less than S0's I, right? So there's a 2 times comparison for each one of the characters here in this prefix string. Then after that, all I need to do is check the length. So if they're equal through the prefix, then the shorter one ends up being the one that shows up first in the dictionary. We saw that from our lexicographic order chart earlier. And so that's where the parts that go on in 9 to 13, that's just a constant amount of work there. So you can say that the big O of this function is going to be big O of min, m, and n. Whichever string is shorter, that's how many characters we're going to be looking at. All right. Worst case time, it's big O of n. Can't do any better than that, right? Like I mentioned earlier, there's no magic way to compare these things. Even if you're not the one writing the loop that goes character by character by character by character, even if you're not the one writing that loop, if you're doing a string compare, that loop is being written. It has to be done somewhere. We can do this with constant extra space. We don't need anything. We have no variables other than our iterator variables. Go back. Where did it go? I just lost the slide. There we go. Okay. I don't need anything more than extra space. I don't need any more extra space. Average complexity for a random string, though, if I'm comparing 2 random strings, pretty often words, there's not a lot of words that have long prefixes in common. So as I'm comparing words in a dictionary, especially if I look at maybe zombie names, it isn't often that I have to go 13, 14 characters in a name to figure out that they're not the same thing. So a lot of times in my average case complexity while I'm comparing strings, it looks like constant time. I only need to look at 2 or 3 characters, maybe 1 character, depending on how different the words are, before I realize that the words are completely different words. So I'm just checking for equality. I can figure that out usually in a constant amount of time. Strings, however, sometimes aren't always random. So you see these comparisons that we have here in the black and red beneath this. I've got 2 different versions of an SQL server. And because of the path that it takes to get to them, it's a while before I get in that string and find the difference. So that's not going to catch my average case constant time there. This one looks like when I'm not using random strings, I can end up with stuff that ends up much more like my average case looking like it's linear time, or getting not so much the average case being linear time. When I'm using not random strings, I'm much more likely to end up in a worst case comparison. Especially if you start looking at words that are next to each other in a dictionary. There because they're already sorted, words that have common prefixes will necessarily be next to each other in the dictionary. So we can see that that's going to show up there as I look at comparing nearby words in a dictionary. Here is the way that lexicographical compare gets handled in the STL. Right? I've got 2 older versions of Lex Compare. I'm just going to say Lex from now. Make my life easier. 2 older versions of Lex Compare, and then the 2 newer C++17 variants. We won't worry too much about execution policy. We'll be more likely to use these 2 versions here. And this one uses a custom comparator. So much like the things that we've done previously in the STL, if you want a custom comparator for those things. So Lex Compare now still isn't limited to strings, mind you. I still have got things that are just sequences. So this will work with a sequence of characters. This will work with a sequence of zombies, right? So as long as I'm working through these containers, it's trying to tell me how this first input compares to the second input. And you can see here the difference between equal and Lex Compare. In equal, we didn't really care where the second string ended, but with Lex Compare, we have to know where the second sequence, I should say, we have to know where the second sequence ends, because we can't determine whether or not we've got a -1, a +1, or a 0 if we don't know if the second string is over yet. So we need to send in 2 iterators per sequence here, so then I can check to see that we are actually lex compare equal less than or greater. In this version without a comparator, of course the STL is going to use standard less on whatever object or data item is in between these 2 iterators. So it's going to use less than here. If you want to use something other than operator less, standard less, then we're going to throw our own comparator in there. The rules of lex compare are pretty straightforward. We've already covered this basically. The 2 ranges are going to be compared element by element. The first mismatch determines which range comes first. So as I'm looking a character at a time, when I figure out they're not the same, that is enough information to tell me which one of these things gets sorted first in the dictionary. If one range ends up being a prefix of another, meaning all of the items in one range are at the beginning of the other range, then the shorter range will end up being the one sorted first. If they're completely equal prefix and length, then that's where we get our 0 from, our 0. And in that case, we would say that either one of them could end up first. An empty range, as we saw earlier in our lex compare hierarchy, is always going to show up less than some non-empty range. 2 empty ranges, of course, therefore, must be equal, because you can't be less than empty. So here's one way that lex compare might be implemented. This one uses, of course, the less than operator. So standard less would have to be defined for your object, or the overloaded operator less than. But this one is pretty similar to the previous one. I've got sort of an empty init for loop. I don't need to do any initialization. All I really care about is whether or not I've hit the end of my sequences. So now my test in the for loop is not only have I got to the end of the first sequence, but have I got to the end of the second sequence. If either one of these 2 becomes true, right? If the first one gets done or the second one gets done, then I'm going to quit my for loop. So once again, this for loop is going through the prefix section, right? And every time through the for loop in my update step, I'm going to increment both of my iterators, first 1 and first 2. As I cruise along here, here's my less than check, and you can see I've got to do the double character check as well. I'm checking if the first thing is less than the second thing, and I return true if that's the case. Then I check to see if the second thing is less than the first thing, and I return false in that case. And I keep plugging away like that through the entire prefix section. If there's anything remaining after the prefix section, if they are not identically length, then I can tell which one comes first just by which one is shorter. And that's what this last nifty little trick does here. What does it say is return first one is equal to last one, and first 2 is not equal to last 2. What did that do? That just did a less than check on to see which one is longer. So say if first one is equal to last one, so the only way I can get out of the for loop without returning is if I've got some prefix thing going on here. And so there's 3 different cases. I've got sort of the first string, and case 1 is they're equal, and case 2 is the second one is longer. Come back. Right, so this is string 1. These are my 3 cases of string 2. And then the third case is string 2 is shorter. So I end up like that. And so you can apply this return statement here, and this actually is going to return true if the first one is equal to last one. So in the case of first one equal to last one, if the both of them are the same length and I've gotten through the for loop, I'm going to return true because those are the same. And if you think of the way that lex compare is going to work here, lex compare is going to say this item should show up less than, and even if they're equal to, right? So if they're equal, I've got to return this bool, right? Because I'm no longer doing a -1, 0, +1. In Lex Compare, I'm trying to figure out how would these things end up in a dictionary. If they're equal, I can put them in the exact same place. But Lex Compare shows up here and sort of looks at the prefix section. Right? And so if they're the same length, I'm going to return true because I haven't found any difference in the for loop. If they're not the same length, and I've reached the end of the first one, then it's more this case right here. And the second string has a full prefix of 1 at the beginning of it and more characters after. So in that case, the first one should still come before as well. So that's how we return true. If, however, I've reached the end of my for loop and I'm in my third situation here, which is where I sort of cut off there before I got to the end of 1. That's where I exited the for loop because 2 is shorter. So then I end up returning false because last 2 is equal to last 2. And you end up with that there. So that's Lex Compare. Make sure you understand it. It's once again another one of those STL style functions where we're working on ranges and doing iterators and incrementing iterators and dereferencing to compare iterators. You should understand this style of code. This is a Lex Compare example. So you can see that it's being applied in this case to a vector of characters. Not the same as a string, very similar, but not quite the same. We don't necessarily get a null terminator there. And we don't get the speed up of saying a vector of characters, that's always going to be on the heap. Whereas a string of this many characters would still show up on the stack. But this version of it, it just generates an MT19937, which is a Mersenne twister for reordering one of these things. And it goes through and compares with Lex Compare the two vectors of characters, V1 and V2. After a compare, it's going to shuffle them until we end up finding a pair of them where we've got them in the right order. And it'll shoot those out and it'll find sortings where we've always got things in the right order. So that's what this example does. Another thing that you should understand, if you don't understand how the random number generator is used there, that's important too. It's great for writing test cases. Those of you who are trying to find test cases, find some bugs, do some solid thinking work there, write a good test case, things that you know are going to direct the algorithm into uncommon situations. But then when you can't find things, write a randomly generated test and see what that'll get for you. So here's an application. How about removing duplicates? So given some container of string objects, what I need is to leave only one copy of each string. And I should leave this container unchanged if no duplicates are present. So how could I do this? I could sort the entire container using STL sort. That would use operator less than. Once the duplicates are next to each other, because if they're sorted, duplicates have to be next to each other, then I can compare neighboring strings using operator equals and copy only the first of the duplicate ones in there. And you're going to accomplish that with standard unique in the STL. So we could do this pretty quickly with a couple of different calls to the STL. Sort them, call unique on it, give me what I got back. This probably should be the cover photo. I remember the first time I saw this slide in this deck, you had always heard the expression, it's like finding a needle in a haystack. And that's not something that you ever visualize. Till I saw this photo and I thought of this guy looking for a needle in this room with his haystack, and it just really made me understand what looking for a needle in a haystack is. So that's what string find is doing in many cases. It's trying to find some string within some larger string. That is the proverbial needle in a haystack. So the way that I can do this with sort of brute force string searching, I can use these two nested loops. And I've got this sliding window. This brute force thing says as I'm looking for ABCA, here's the search, the thing that I'm looking for, and then the destination I'm looking within is this body here. So brute force is you start out and say, well, is A equal to A? Yeah, that's good. Move on. Is B equal to B? Yeah, that's good. Is C equal to C? Yeah, that's good. Is D equal to A? No, that's not good. Okay. Now, I know as a human that I can move quite a bit farther along down the line just from looking at this particular example. But as an algorithm, it doesn't know that ABCA might not start here in the very second position. So that's where this sort of sliding window is sort of given this title. We're looking at a window of size 4 inside the searched string because the search string is 4 characters. The string that we're searching, we look at that 4 characters at a time and see, hey, does what we see through this window look like what we're searching for? So the sliding window moves over 1 character. Now we do this comparison for ABCA and the second 4 characters. That one drops out pretty quickly. We see that B and A automatically fail. So in constant time, I can move my window over 1 more spot. Now I'm trying CD space A, and that one doesn't line up with ABC either. But in order for me to make sure that I don't miss it, I have to check for this window starting at every character in the string that I'm searching. Worst case time on this is I've got some big O of length of needle times length of haystack. Right? And how do I calculate that? That means that I'm looking at the length of the short string at every possible beginning place within the long string. Right? So that's the worst case comparison. So you can imagine this example here, finding 5 A's followed by a B in this string of 25 A's followed by a B. And yes, I just made up 25. I don't know how many A's are there. There's a bunch though. So there's the needle in a haystack. So for each one of those, I've got to go A, B, nope, move over. A, B, nope, move over 1. A, B, no. So that's my length of needle. That's A, B. And I'm going to do that in each one of these new starting locations, length of haystack. So in the brute force method, then my searching worst case complexity is going to be length of needle times the length of haystack. In the average case, however, we know that this ends up being something more like len haystack, and it's easy to see why now that I've got this sort of example in front of you. You see, in the first particular window comparison, I do look at 4 characters before I find a fail. But then as I move through the string, I see right away B doesn't work with A, C doesn't work with A, D doesn't work with A, space doesn't work with A, and so I can, in many of those cases, just move 1 character, check 1 character. So my average case ends up being length of the haystack. The inner loop, in that case, is only performing 1 comparison because as I move the window, the outer loop moves the window that I'm looking at within the searched string, and the inner loop looks at characters in the searched string with the characters from the search string. So my average case ends up being len haystack. So that's better than my worst case there. In brute force string searching, the STL is often going to sort of just use this straightforward sliding window thing. It's pretty fast because average case is len haystack, right? Can't get much better than that. If we've got to search something that's got n characters in it, and we can get it searched in n time, it's hard to beat that. However, when I do have realistic situations where I can come up with common strings, and you would find this when you're trying to compare documents, for instance. Trying to see if a particular essay has got some copied section of another essay. I'm running into something that's much more like a worst case scenario. When that's the case, we've got another method of speeding up this search that's better than brute force. And what it's going to end up giving us the complexity of is a big O of len needle plus len haystack, where the worst case is len needle times len haystack. Now if I can just add the two together, I can end up with something that's quite a bit shorter. And this is done with some pre-processing, so it's not as fast on most strings, but we can do some pre-processing, and then that will speed us up as we work our way through this. And the KMP algorithm is an example of that. The Newton-Morris-Pratt is a string searching algorithm that ends up better than brute force. And the idea here is we're going to speed up the inner loop the best we can. So most of the time we'll end up with most of our equal comparisons fail in constant time. If we can get that fail to happen in constant time, then we can make that Len needle sort of inner loop drop out. We're not working through the length of the needle in the inner loop. We're just working through the length of the haystack. So that's what this is going to do. The worst case complexity is still similar, because I will run into situations where I might have to break down and do a full check, but it's a lot harder to get to a worst case scenario and much more rare in practice. So how do we speed up these equal comparisons? The idea we're going to use here is called a string fingerprint. And this gets us into our hashing. I said we're going to touch on hashing with strings. So string fingerprinting and hashing have a lot in common. So the big idea here is for each string, I'm going to compute some number. There you go. That's hashing. I'm going to take the string and convert it to a number. When I know that I've got these conversions, just as in hashing, I can say if the fingerprints are different, if I take two strings, calculate their fingerprints, if those two integers, those fingerprint integers, if those integers are different, then I know right away that the strings must be different. So what I have there is a necessary condition, right? It's necessary that if they're different, then the words are different. However, when the fingerprints match, then the strings can still differ, but it's much more rare. So when I have a situation I'm looking at two fingerprints, I can very quickly, in sort of constant time, compare the fingerprints, because now the fingerprint is an integer. If I can compare the integers and say, hey, these integers are different, I know for a fact the strings are different. If the fingerprints are the same, then it's still the case that the strings might be different, but they might be the same. And actually, they rarely differ when the fingerprints are the same. So I get this speed up by saying I can take a quick look and check the fingerprints, and only when the fingerprints are the same do I have to do the character by character check to make sure that they actually are the same. The numbers, we really don't care what the number values are. We don't store those as a descriptive thing. We just use them for the comparison, though. A bunch of different fingerprint functions exist. We're going to look at a simple one here, and you could use this in your mind to figure out how hashing of strings would work. So, for example, I could take a simple one and say each one of these characters is really just an integer in the computer. It's just an ASCII character, or at worst, it's a Unicode character. It's a byte or 2 bytes worth of integer data. I could just add all of those things up. So if I was just sticking in simple ASCII, I take this string and add up each one of the bytes of its characters, and you see that the fingerprint function would work across some strings, but other strings it's not going to work here. We've got a nice Harry Potter example with Tom Marvolo Riddle, the name that Lord Voldemort used, or he gave himself Lord Voldemort from being Tom Riddle, right? So if I were to take those characters and use my simple fingerprint function of add up all the characters, I would see that they're equal. So I need something that's going to give me something a little bit better, because I can think of a lot of short words that have similar characters in them. We'll see an example here like tops, pots, spot, and stop. Tops, pots, stop, and, well, there's post in there. There's a bunch of them, right? So all of those words have the same 4 characters in them. If I would to use a fingerprint function on them, that's quite a bit simpler than the Tom Riddle example, but still a much more common thing that I might find. It's hard to determine those with that simple fingerprint function. So the application of this fingerprinting is, if I've got these n strings, I can find the duplicates by comparing their fingerprints as opposed to comparing them n characters at a time, m characters at a time, right? So if I got, so the example is I've got n strings, each of them with some m characters, and rather than doing this quadratic comparison of every character of every string to every character of every other string, if I were to calculate the fingerprint of each one of those n strings, that's sort of the pre-processing step in many of the examples I've talked about earlier. If I calculate the fingerprints of these strings, then all I have to do is compare the fingerprints. And I know that because of the way I calculate my fingerprints, if the fingerprints are different, then the strings are absolutely different. And it's only on the rare occasion when I find two strings with the same fingerprint that I have to do a character-by-character comparison. All right? These fingerprints can really help a lot. You can use this to find duplicates and all kind of good stuff. So this is what the Rabin fingerprint looks like. Rabin is named after the computer scientist who came up with this, right? So the Rabin fingerprint says, instead of just adding up character codes, let's combine that with the position of the character in the string. Why this is something that you're very familiar with is because you know the difference between the value of the number 1, 2, 3 and the value of the number 3, 2, 1. One of them is 123, the other one is 321, and you know intuitively which one of those is bigger and which one is smaller, and that they're not the same. Even though they have the same 3 digits. How do we know they're not the same? Because of where the digits are placed. And so in the Rabin fingerprint, it does something similar. It says, rather than just take the ASCII value of the character, take the ASCII value and combine it with its position. And then we'll be able to make a fingerprint that has more information encoded in it and allows for fewer collisions of similar words here. So in this particular example, we're just going to use in this particular example, we're going to use a simple value like 10, just because humans think in tens most often. 10's an easy way to do this. So I wouldn't actually use 10 in a real Rabin fingerprint. I would use a larger number here, but I'm using 10 just to make this simple. And so you can see the ASCII codes for Tom Marvolo riddle start out like this. It's something like 84, 79, 77, that's TOM. 32, of course, that's our space character. M again is another copy of 77. Rather than just adding those up, I'm going to create this sort of running fingerprint. I can take a value, 84, and as I add the next character O to it, all I have to do is multiply my current value, which is in this case just 84, and add 79. That's my new fingerprint of TO. Then to get the fingerprint of TOM, all I have to do is multiply the fingerprint of TO by 10 and add the next character. And so that's how this fingerprint works. And you can see how shuffling these characters around would usually change the result. Because by the time I get done here, we see this 84 that was in the first position has been multiplied by 10 3 times. If I put that in some other position, now 84 has a completely different contribution to the total value because it's in the third position or it's because it's in the second position. So shuffling the characters usually changes the result, and so that's why the Rabin fingerprint is so successful. And I said here, base 10 is used just for illustration because we know how to multiply by tens. It's easy for us to think that way. We would like to use prime numbers or something at the very least that is larger than the total number of characters in my alphabet. So that's what I'd like to do, is get some prime number. So when I say that, I mean, so if I'm working on lowercase ASCII characters, there's 26 of those. I would like some prime number that's larger than 26. So the first one of those is 29. So if I was sure that I was only going to use lowercase characters and I was writing my own Rabin fingerprint, I would probably use 29 to get me past that. What if I was using uppercase and lowercase? Now I have to get a prime number past 52. You can do the math, right? If your character set keeps extending, if you're using Unicode, whatever you're looking at, that's what you're trying to find something there. So the Rabin fingerprint now ends up using the position of the character to calculate the fingerprint. And I can do a sort of sliding window thing with a fingerprint. So if I've got some string like this, right? Say I've got a fingerprint of these first 5 characters. If I've already calculated that, F, right? I can say that in my current example, I'm multiplying by 10. I will have multiplied T here by 10 4 times. 10 to the 4th. So I can take F and remove T times 10 to the 4th and add A, right? If I add A and multiply everybody in F by 10, then set, there we go, set plus, shoot, I get this simpler there. I get my formula written out. So I take F and I'm going to subtract T times 10 to the 4th, right? I can take that whole thing, multiply that by 10, and add A. All right, so that's how I can sort of slide my fingerprint window. So I can do sort of my pre-processing, get a window as wide as my search string. Then to move that fingerprint over by 1 character, I can do that in a constant amount of work. Because all I have to do is remove the largest character, slide the shorter window over, and then extend the window back up to the original size. So I take a 5-character window, I shrink it by removing the first character, make it a 4-character window. Then if I add the character after that, now I can extend it so that I've got a new 5-character window that is slid over. What that lets me do is I can in constant time calculate a new fingerprint of the area that I'm searching. So if I'm looking for a small string within a larger string, here that's what Rabin Karp string search is I first calculate the fingerprint of the needle. That's not ever going to change because I'm always looking for that particular term. So I calculate the fingerprint of the needle, then I calculate the fingerprint of the first needle number of characters in the haystack, and I can compare them right away. If they're not the same, then the haystack doesn't start with the needle. The needle's fingerprint won't change because the search string doesn't change, but the thing that I'm searching does change, so all I have to do is do a constant amount of work to slide the haystack needle over by 1 character, and then do a constant amount of work to compare the new fingerprint to the needle's fingerprint. And I can figure out that way that at every starting location in the haystack, if I can get there in a constant amount of time by adding a new character and removing 1 old character from the fingerprint, and then doing a constant amount of work to compare the 2 fingerprints, this is how I end up with this big O length of haystack search string, or search complexity. So first we compute the needle's fingerprint. Then I check to see if the haystack starts with the needle. If the window is equal to the prefix of the haystack, then I'm good. If they're not equal, then I can move on, right? If I move on, all I do is incrementally update the window. So I remove the oldest character and add a new character, which I can do in constant time. And I can once again do a check there. If I end up with a fingerprint of the window equal to the fingerprint of the needle, now is when I need to do a character by character check. And since we're saying this happens rarely, I don't end up doing as many of these character by character checks. You can repeat this until you do the entire search, and this is what ends up giving us our big O of Len haystack algorithm here. Okay, as we look at these long strings and I'm fingerprinting them, you might be thinking all of this multiplication and addition could lead us to overflow, and you would be correct. So we can be pretty careful with that. All we have to do is just replace our conventional arithmetic, multiplication and addition, with modular arithmetic. So anytime I increase this value, if I mod it by something, I can keep it within a particular range. And this is typically done with some largish sort of prime. Here, the example given is 3355439. That's a largish sort of prime. I don't know how long it would take me by hand to find a prime number that's in the 3 millions. But it's not a small prime. That's what I'm saying. So every time I add a new character at the beginning, I would mod by some prime there, and that would keep my value in a particular range and keep me from overflowing. We get the same sort of thing. We see the example here as we look at a clock. If we say it's 11 o'clock in the morning, if we're not using military time, when we plus 4, then we plus 4, we get 15, mod that by 12, and you say, well, now it's 3 p.m. So 4 hours after 11 is always 3 o'clock. Doesn't matter whether it's a.m. or p.m. 4 hours after 11 is always 3 o'clock sometime. So 11 a.m. plus 4 is 3 p.m. 11 p.m. plus 4 is 3 a.m. That's just modular arithmetic. So if you want to avoid overflow in your fingerprinting, then every time, as I mentioned, you do a multiplication or addition where you're multiplying and adding, then you're going to mod by some value to keep it down. And the arithmetic still works the same in terms of the comparison and the calculation and the division out of other items. So that's how we avoid overflows. This piece of code here that you see is a Rabin-Karp search. And you can get out of it the worst case complexity now is going to be a big O, or average case complexity now goes to a big O of len needle, that's this section, plus this section, which is len haystack. All right. And so let's just take a quick peek at it. And you can see here, this first for loop goes through and calculates. I've got my inputs. What are my inputs? The string input is needle, and the string input is haystack. And I've got some prime number. I'm going to use that prime number as my sort of mod in my modular arithmetic. Right? So N is the length of the needle, big N, capital H is the length of the haystack. So I'm going to run through the first N characters of both the needle and the haystack and calculate their fingerprint. And all I'm doing here is taking some base value here, multiplying by N as I work my way through and moving on. So in the Tom Marvolo example, we were using 10. Here, I said we can use a prime number that's larger. In this case, we're using a base of 128. And sometimes you'll use a number like that because when you multiply by a power of 2, that's faster than general multiplication. We can do a bit shift there. So in this case, a base of 128 is used because it's fast. And 128 is chosen because it's a power of 2 that is larger than my ASCII character set, right? ASCII character set has about 128 characters in it. So that's going to move me past anything in ASCII character set because some of those characters aren't even printable. So every time I get a new value, I'm going to multiply the old value, a new character. I'm going to multiply the old fingerprint by this base and then add a new character. Multiply by base, add a new character, multiply by base, add a new character. And when I increase that, I want to make sure that I mod it by some prime number so that I don't have overflow. So in this first for loop from 6 to 9, you see that we're calculating these two fingerprints. And I end up, after this loop, with a fingerprint of the needle, N, and the fingerprint of the prefix of the haystack, or the first needle length window in the haystack. That's my two fingerprints. So N and H are those two fingerprints, and then I jump into this additional for loop that's going to allow me to slide that window throughout the haystack. So my first check is, hey, if these two fingerprints are equal, now I have to do a byte by byte comparison to see if they're actually the same. If they are the same, then I've found it, right? I can return where I found the thing. If they're not the same, then I'm going to try to extend that by just sliding the window over. As long as I haven't hit the end of the window, or the end of the window hasn't hit the end of my haystack, then I'm going to modify the haystack's fingerprint by removing the first character in the haystack, multiplying by the size, and adding a new last character to the haystack. Or sorry, I remove the first character of the window, multiply by my base to increase it, and then I can add a new character at the end of the window. So I get a new fingerprint of sliding that over one. Mod by prime to keep it inside bounds, and then I can do my comparison. So this is the Rabin Carp string search. Complexity, of course, when I've got different substrings and I never get equal fingerprints, I just run through that whole haystack and I never match up, and I can get that done in haystack time. Every time I've got a collision, it's going to cost me needle time to perform that equality check for the substrings. But since these are fairly rare, it doesn't actually happen a lot of times with most strings. It helps to choose larger primes to keep my modulus Q there. And then I saw that my base was chosen as a 2 to the K with something that ends up that's something that can help me with bit shifting. All right. That's strings and sequences.